Now that we have started on representations, let's talk about the reducibility of representations. This is a very important idea that, like those of you who did some quantum mechanics with me, did you do Clebsch-Gordan coefficients and the, how you can combine spins?
Yes, sir.
And then you can write those in terms of, what are known as irreducible representations of the spin group. So basically, what we're about to discuss is kind of that idea in abstract. Okay, so let D be a representation of the group G. Okay, so what does that mean? That means that if you have, say, G1, G2 elements of the group such that G3 is equal to G1 times G2, then D as a function of G3 is D as a function of G1 times G2 is equal to D times G1, G of D1 and G of D2. That's what it means for something to be a representation, right? So these are for definiteness, we take this to be a matrix representation. So let D be a matrix representation, okay, of G. Now, if there exists for all the elements of G a matrix S, now S has to be independent of G, such that G tilde of G, D tilde of G, which is defined to be S inverse of D of G S, such that D tilde takes this form for all G. So then we say D is a reducible representation. Okay, if such an S doesn't exist, if such an S doesn't exist, then D is an irreducible representation. In short, irrep. Okay, so basically what I'm saying is that you have some matrix D, which is a representation of some group, and you find some similarity transformation such that it takes this particular form, then we say that it's a reducible representation.
So is D tilde 2 times 2 matrix?
Sorry, is D tilde what?
A 2 times 2 matrix, or is it a block representation?
Oh, it's a block diagonal matrix. Sorry, it's a block matrix. Yeah. So these are all blocks. Sorry, they are not two-dimensional. So they're all blocks. It's a good question. Okay. Now let's make some comments. Comment number one is that for a reducible representation, say d tilde, we have d tilde of G times d tilde of, say, G prime. So what is, so each of this matrix has this form, right? A of G, 0, C of G, B of G, and then A of G prime, C of G prime, 0, B of G prime, right? And then if I multiply them, I get AG, AG prime, this is 0. Here we get BG, BG prime, and here we get AG, CG prime plus CG, sorry, let me, CG, BG prime. And of course, because these are all representations, we have A, GG prime, B, GG prime, and we can define this to be C, GG prime. Okay? So note that for reducible representation, the action of the smaller representation, A and B representation, on some vector space, say VA, on some vector spaces, say VA and VB, do not mix VA and VB, right? Whereas this guy does. Okay, so we are actually not that particular part of the matrix. So that's comment number one. Comment number two is that for finite groups and compact Lie groups, many of the results for finite groups, go over to compact Lie groups. So for finite and compact Lie groups, one can choose, one can show, and it's a theorem, we won't show it, that C can be chosen to be 0 for all G. So if that is the case, then we say that D is completely reducible. Okay? Or decomposable. And these are the cases that we usually deal with for compact Lie groups. Okay, so we don't have to worry about that pesky C off-diagonal term. So for all effective purposes, we can take reducible matrices to look like this. Okay, there could be more factors, This could be further reducible, right? This could be further reducible. Okay, any questions?
Sir, I didn't quite understand the first comment where you wrote additive, like added quantity into CGG prime. So how did you go there?
Well, I'm just defining this to be this thing.
Oh,
This is not really a representation. These are. I guess they do have some mathematical structure, but they're not, that's not in, we're not interested in them. Okay, by definition, this is basically this thing. But as you can see, this is not a representation, right? Okay, any other questions? So while we are talking about representation, let's talk about the unitarity theorem.